computational.
Thank you, Dr. Z. Welcome to the talk. So, I have notes, and I'm going to get lost if I don't read them, so ignore the paper in my hand. So this is the abstract abridged. I'm not going to read it to you. But basically, in this talk, what I'd like to present, maybe I'll turn this off in a minute. It's sort of going to come in 5 parts. So first, I'm going to talk a little bit about the historical background, introduction to this type of problem. Then I'll talk about some of the old results, so specifically particular theorems or other things that people have already proved up until recent history. Then I'll talk about new results, where I'll mostly allude to some of the work that I've been doing and talk a little bit about where it fits in the big picture, rather than list lots of theorems. I'll just talk about them. Then I'll talk a little bit about the methods, the tools that I've been using, some of the older ones and some of the ways that maybe we can adapt or innovate away from those ideas. And then we'll finish up with a conclusion. So I guess parts 1 and 5 might not be sort of like a 5-paragraph essay from high school. But in the conclusion, I mostly want to talk a little bit about future directions and ideas, and some of the questions that I don't address on my own, or that I'd like to address in the future, but that are pretty open-ended. So that's where I want to start. So. So my clicker doesn't want to work. So this all started with Isai Schur, who proved what is arguably the first result in actual Ramsey theory, that is before Ramsey's theorem. And what he proved is that for any R, so throughout this talk, R is going to indicate the number of colors. Does the laser work? No, the batteries must be dead. So R is going to indicate the number of colors, and when you take the positive integers and you assign each one of them one of these R colors, there is a monochromatic solution to x plus y equals z. So if you list out every single positive integer, and then you assign every single one of them some color from a finite set of colors, you'll be able to find 3 or potentially 2, in the case that x and y are equal, that are the same color that solve this equation. And there's a finitary version of this statement, which Dr. Z, you should appreciate, which says that you don't need an infinite set to do this, because there is really some n, depending on R, so that if you go out just that far, you'll still find it. So in this case, we know some of the values of that n, and that n is usually called the Schur number because it corresponds to Schur's theorem. Okay, so what this says, S1 corresponds to 1 color, which doesn't really mean anything. So once you get to the number 2, you have a solution, 1 plus 1 equals 2, and since there are no other colors, they have to be the same color. We'll talk a little bit about how to figure out that S2 is 5. But what this guarantees is that this number is finite, that there is a point of no return, so to speak.
That is as far as people know?
Yes, this is labeled as hard, and many other labels in the encyclopedia, because this is it. We have bounds on some of the, we have some bounds that apply for all R, but we have some specific bounds for the next couple of numbers, but that's about it.
Could you say what the 14 means? If you have more than 14, something. What?
Okay, yeah. So here's what it means for S3 to be 14. If you take the integers 1 through 14, all of them, and you assign them one of three colors each, so red, blue, red, blue, whatever, somewhere in that set will be a monochromatic solution. So some people like to take this sequence and subtract one from every term, where they're just doing the off by one version of that.
And if you have more than 14?
It should still work because you can just ignore 15 and beyond.
Less than 14 doesn't.
Right, there is a coloring.
Okay, yeah.
There is a coloring of 1 through 13 that does not have this property.
Thank you.
And of course, X and Y are supposed to be distinct, right?
No,
No?
no. We're allowing repetition.
Oh, okay.
There are some theorems that sort of talk about how you can force them to be distinct. It's still true. These numbers will potentially get bumped up because it's a little bit harder to do that. So, Richard Rado, who was a student of Schur, this is him, took Schur's theorem and basically said this can't be a phenomenon exclusively associated to this equation. I mean, this is a very easy equation, but there are lots of equations that are easy. And he decided to look at homogeneous linear equations. And what he said was that this has the same property, the monochromatic solutions, if and only if some subset of the coefficients sum to 0. So x plus y equals z. If you move the z to the other side of the equation, that's a -1 coefficient. So 1 and -1 sum to 0. So he generalized it in a very big way. I won't talk about it, but he also generalized it to systems of homogeneous linear equations, where the condition has to do with the columns of the matrix associated to that system. It's a little bit more technical than this, but he did a lot of work to push that further. Yeah?
So can those AIs be any real numbers? Or
They should all be integers, sorry.
Okay, integers.
I should be clear. So when we're looking at this, we require them to be at least rational, because if they're rational, we can clear denominators and make them integers.
Right, okay.
Yeah, thanks for that question. I kind of glossed over that. And what we're going to do is sort of set up a notation where throughout the talk, if I say curly E, that just means a linear homogeneous equation. And I'm going to impose one condition, which is just sort of a time saver, which is that I want the coefficients to be in this order. None of them should be 0, because then they shouldn't be there. And at least one of them has to be negative, and at least one of them has to be positive. If that's not true, there are no positive integer solutions to this, and that's sort of a no-no. Why would you talk about monochromatic solutions if there are none? So when we want to talk about this equation, what I'm most interested in is the quantity associated to that, which is this minimum n that gives you a guarantee of monochromatic solutions. So if you take the coefficients, and we'll try to list them in order, I'm using R for Rado number, little r for number of colors, and then just a list of coefficients. And I'm repeating this m here because in some cases where we like to use ellipses, you might need to say m. And that will give you a formula in terms of m. Is the notation clear? This is not necessarily standard notation, but there actually, as far as I know, is no standard notation. Some people just put the equation in here, but that has its own issues about consistency and canonical representations. So here are a few examples. So here's S3, the one we talked about being equal to 14, and that would be -1, 1, 1. So here the z becomes negative, and since we're listing them in order, it comes first, 1, 1. And there's a list of others. The first few of them, these are all two-color Rado numbers. And you can see this one is 7, this one is infinity, this one is 4, but this is the same equation with 3 colors, and that's also infinity. What that means when I say infinity is the minimum n doesn't exist. It means that the theorem of Rado doesn't work here because there's no subset that adds to 0. Right? Here, same problem. But that's not a guarantee that it doesn't exist. So for 2 colors it works, for 3 colors it doesn't work, and then for any higher number of colors it also fails to work. And this property is called regularity. Regularity is a word that's used in sort of generic Ramsey theory a lot. They talk about partition regularity if they want to really use the technical terminology. And the idea here is that if this number is less than infinity, if we can really make a statement about the monochromatic solutions, then we say that that is regular. So R regular means it's regular for some specific number of colors, and just regular means it's regular for all R. And for some equations, like on the previous slide, which I can click back to, this is 2 regular, it is not 3 regular. Right? So in particular, it just sort of stops working once you get to 3 colors. And some equations then have a degree of regularity we associate to them. And this sort of veers a little bit away from where we're going with the results, but is an important observation. There is an equation that has exactly degree of regularity R for all R. So there's some stratum that every equation falls into where either it's regular for all R or it's regular for a specific R. But these are distinct classes. There's somebody who just gets 1 degree higher than the rest. This is the example. It's a bit of a messy formula, but the easiest way to write it is with rational coefficients. You could clear the denominators and then it would be integer coefficients. But this is kind of the witness to some hierarchy of regular equations. So Rado's theorem, sort of restated, says an equation E is regular for all R if and only if there is some subset of the coefficients that adds to 0. But Rado had another theorem, and this theorem is really the one I like. It gives me a huge guarantee. Any reasonable equation is 2 regular. So if I limit myself to 2 colors, as long as I have 3 variables, and I obey these conditions, which we said are just sort of triviality conditions, as long as I have 3 equations, it's regular. And of course, if it doesn't, then you can get into trouble with something like x equals 2y, which is not reasonable, according to what I've defined reasonable to mean, and it is not 2 regular. So the major question might be, why are you interested in this? And my answer to that would be, well, first of all, it connects with Ramsey theory, which is sort of at this point, I would say a classical part of combinatorics, something a lot of people have interest in. And it's a fairly rich subject. As I said, Rado proved it in greater context, systems of linear equations, non-homogeneous equations, which I'll talk about a little bit. Van der Waerden's theorem can be re-expressed. An arithmetic progression satisfies linear equations, so you can translate between those contexts. Additive combinatorics, basically by way of Ramsey theory, is connected to these questions as well. And there's number theory hiding in here somewhere. If we forget about colors, if we only have 1 color, just asking whether an equation has solutions, which is what this is a number theoretic question. Obviously, for linear equations, that question is not hard. But for nonlinear equations, there could be a lot of juicy number theory content embedded in here. So much of it that it makes the combinatorics very difficult, even for 2 colors.
It's undecidable in general.
Sure, in general, it's undecidable. So there are huge families of Ramsey theoretic questions that are undecidable as well for that reason. So some of the directions this research takes: the degree of regularity question, which I pointed out there was a big theorem in 2009 that sort of established that that was a meaningful classification. There are a lot of structural Ramsey theory statements, infinitary combinatorics, and sort of highbrow, abstract statements you can make. You can do results for systems of equations, recurrences, which are themselves sort of systems of equations. And then what I want to talk about is proving various values for these Rado numbers, specific values. So there are some basic results which we talked about already. The first sure number is 5, the next one is 14. I'm not sure who proved that, if it was sure or if someone just sat down and did it, because you can just sit down and do it. It's not too hard. There are a lot of other computations that aren't too hard, where we assume at some point someone sat down and did it by hand. But it's not worth publishing because you just sit down and do it and it's done. This one is tough. In 1965, using something we might call a computer, although these days it might be unrecognizable, Baumert proved that the fourth sure number is 45. And I'll talk about how we're still using that methodology today.
You mean his computer proved it?
Yes, he asked his computer to prove it, and his computer was nice enough to oblige. And the fifth one, this is unknown.
Since 1965, they can't even...
No, and part of it is the lower bound that we know for that is roughly 160, I don't know, it's give or take 1 or 2, it's about 160, which is quite a bit bigger than 45 when you consider the exponential numbers of things you would have to check.
Does there exist a purely human proof of the 45?
I don't know exactly how you would define purely human.
Yeah.
I could certainly write down what the computer tells me. I wouldn't call that a purely human proof. I don't think so.
Humans check it better than me.
Humans
Sure,
can certainly
sure.
check it, and it's very easy to check that your code works. So in the sense that there's a computer verifiable, or a human verifiable computer proof, yes. A human could read the code, agree 100%, and then...
No, but the output itself, without the code.
Yeah, it would take you a while,
Yeah.
but you could.
Yeah, checking it not exponential, checking its polynomial time.
Yeah, in the length of the app, yeah. So, starting in the 80s, a few people wanted to sort of look at this in more generality, where instead of just doing one equation, which isn't really much of a result, we wanted to look at families of equations. So here's a family of equations, x plus y equals az, and the answer is binomial coefficient, which should make us combinatorialists happy. We love binomial coefficients. Burr and Liu actually never published this paper. There's a preprint that allegedly someone had. I've never seen it. I don't know where to get it, but all of those results have wound up in other people's papers because as people moved forward, they started proving more things. So most of Burr and Liu's results are published in other people's papers, but they apparently had a nice manuscript that sort of started to probe into this area. A couple of other results along those lines. Here, now x and y, it's ax plus ay equals 2z. Ax plus ay equals a plus 1z, where I guess that agrees if a equals 1. Except that's not valid, unfortunately. So one observation that you can make is that these are all polynomials. And that tends to remain true regardless of the problem that you're working on. Here is a set of results where now, instead of changing around the coefficients a lot, we're going to focus on long lists of coefficients. This was one of the first results, and these are often called generalized sure numbers because all they're doing is adding extra terms. X plus y plus z plus w plus v plus u ... equals some other letter. And there, it has to depend on something. It depends on m. And it took a long time, but somebody managed to make a huge leap in generality where all but 2 of these coefficients could be anything. And they have this nice expression that's, again, a polynomial in the coefficients. And then a few years later, they got one more of the coefficients pinned down. And again, still a coefficient. Yeah.
Oh, I was just pointing out to myself that, but A1 still is positive.
Yes,
so.
A1 still has to be positive. So in some ways, if you think of the left-hand side and the right-hand side, all of these have sort of increased in generality, but the left-hand side or the right-hand side is always just z. So on the opposite end of that coin, here, and maybe I'll just get the color highlighting there a little bit. Now we're changing the coefficient on z, if we're going to call it z, 1, 2, or 3. And we've also got, as a nice sort of bonus, a parameter k, which is the coefficient on one of the other terms. And here, there's an explicit quadratic. Here, this is also an explicit quadratic. It's a quasi-polynomial. So mod 4, there are 4 different polynomials that this follows. So if k is 0 mod 4, it's this polynomial. If it's 1 mod 4, it's that one, and so on. Here, same thing. Now, there's some more quasi-polynomial terms. And the period of this is not 9. You'd think the period of this is 4. The period of this should be 9. It's 27, which makes me a little bit scared that if you change this to a -4, the period might be 64 or more. I don't know. It could be enormous.
256.
So one thing that does strike us as perhaps more interesting is that you can sort of pin down the high-order term. And that is something that I've worked on a little bit, is proving that sort of in general. If you have a here, minus a, this should be k squared over a squared. And a couple more results, sort of combining those two ideas. Now you have many different terms on one side, and you can change the term on the other side. And here, there are explicit formulas which are quasi-polynomials when you have floors within floors within floors, or ceilings. Those are ceilings. That depends on the modulus, so it's still a quasi-polynomial, just written in a different way. So here, this is kind of a really interesting result, because now, for the first time, one of our coefficients shows up in a denominator of a floor, but it's still in a denominator. So something else is going on there. And just as a sort of a sample of the other stuff that's a slightly different flavor than what I tend to be interested in, there are plenty of non-homogeneous equations that people have studied. And here I don't have a standard notation, so I'm abusing it a little bit. All of these, if you set c equal to 0, you get a previous result that we've had. So here, if you set it equal to 0, you get that m squared minus m minus 1. That was from 82. So 11 years after that was the homogeneous version. So the question is, where does this put us? If we're trying to move forward with this research, there are a bunch of different cases where you can change some things, but not all things. One of your coefficients has to be small, or a bunch of them have to be 1s, or there can only be 2 or 3 variables total. 3 or 4, there shouldn't be 2. And in fact, people have gone out and just taken a single nonlinear equation and computed its Rado number. And even that itself is kind of a substantial feat, because we have no guarantee that it has a finite Rado number. So there's a little bit we can do here, and there are a lot of things we can do with greater than 3 colors, where you do a few computations and then it becomes intractable. So we can try to compute anything, but of course if we don't do it carefully, the computer just crashes. So that's where everything sort of picks up for the new results. Now before we talk about what the results are, I think it's more important to talk about where equations live. If we're studying squirrels, then we also have to study the forest. Do they live in a forest? I don't know. We study wherever it is squirrels live. And here, if we're studying equations, and in particular the solution sets of equations, then we have to study where those solution sets live, what their structure is. And everything in the world, I think, could be described as a hypergraph. Here, the vertices are the numbers 1 through n, And the edges are the solution sets to some particular equation. It's not uniform because we allow repeated, like x and y could be the same. It's not regular in any way. It lacks a lot of the structure that we might like in a hypergraph. Hypergraphs can be incredibly generic and abstract, so without a lot of structure, knowing where they live doesn't help us out too much. But there is one way we can relate equations to each other, and there's a technical explanation here. But the idea is if I take an equation, and I'll just write out an example. If I take the equation 3x plus 5y plus 2z equals, let's say 12, equals 7w. That has a particular solution set. There are a bunch of quadruples and a few triples and a few ordered pairs maybe that fit this equation. And what I'd like to say is that that solution set also occurs if I say combine these two terms. If I just assume that x and y are equal, then I get an equation that looks like, oops, shouldn't be, it's 8x plus 12z equals 7w. Any solution that I have for this will also give me a solution for this, where one of the coordinates is just repeated. Okay, so if I had xzw as a solution here, I should be able to just reuse x to get a solution here. So that gives me sort of this statement here. Solutions to the new equation, E prime, are solutions to the old equation. The opposite is not necessarily true. The converse will not hold. So that has to increase the Rado number, because you have potentially fewer solution sets. Your Rado number will go up. So we sort of define a partial order on equations according to this structure. As an example with, oh, I should turn that. As an example, if we take this equation, we set w and z equal to each other. On the right-hand side, the Rado number here is 4. The Rado number here is 9. And I'm using the two-color Rado number because I don't have to worry about whether or not it's infinite. So it forms a partial order. You can prove all the usual axioms about partial orders. It agrees with hypergraph containment. One edge set is a subset of the other edge set. And it's monotone with respect to this function r. And now what I want to tell you, I just said that, it's monotone. And it allows us to prove, wait, did I? Oh no, I didn't. So it allows us to prove upper bounds and lower bounds, not just for a single equation, but all the way up or all the way down the partial order. It tells us where to look, and this is basically a formalization of some ad hoc methods that everybody uses, but nobody really acknowledges. All those equations where they have m different terms, they always just combine them into two terms. So we're trying to get a handle on that, and I'm taking a cue from Eddie here. So here is what I'm going to call the big picture. This is a map of all the results I could dig up that sort of fit into this picture. So green arrow stands for generalization, where this family of equations is strictly more general than that one. Here it's bz, here it's 2z, for example. The red corresponds to this reduction by collapsing variables, and it could be written as a poset, but the chalkboard was the wrong shape for that, so it's a little bit of a winding directed graph instead. But here you can see all of the results that I could dig out in the literature. So what I want to say is you can't read that. Is they're grouped by families, not by single equations. That would be too wasteful.